So we have seen this formulation in terms of the second P-L-R of stress. So I'll just write that here. Rho 0 times del square chi by T square is equal to del dot Fs plus rho naught times V naught, and Fs and naught is equal to cofactor F times N naught times T. And we have also seen that the second P-L-R of stress is symmetrical. So this is the formulation, and so suppose if we, so one example is solved in the book, you can take a look at it. So it's like a rotating bar example. So if you actually solve this particular problem in the deformed configuration, then we have to ensure that suppose this end is going to be stress free, right? So this here there is no traction that is applied here. So here you will have that tau is equal to 0. So this tau is just a one-dimensional stress component that is normal to the end of this bar. So this traction here on this particular edge is 0. So we have to ensure that this traction free condition is applied on the deformed configuration. So suppose if L was the original length, okay, so I am just drawing it dotted, and then this is delta, then this tau at x equal to L plus delta is equal to 0. So that is what you have to ensure. So this is your x, suppose. We have to ensure that this, so we do not know what this delta is. That is something that has to be solved for. But so it can be an iterative process to, in order to basically solve for this delta and apply this boundary condition. But so that formulation is given in the book, and you can take a look at it in the book. Fine. Then there is another section in the book on the variational formulation also. So that part also I will not cover in this particular course. The variational formulation is actually very, very useful for the finite element formulations. Okay, so that as I said that for our purposes here, the variational formulation is not going to be all that useful. But I will just indicate what you get basically as the variational formulation, so that you can make an analogy with the general variational formulation for linearized elasticity. So here the variational formulation comes out like this. So z dot del square chi by del t square times dv is equal to minus s of e delta plus rho naught times z dot v naught times dv plus integral z dot t bar naught times ds. This is over s naught of t. So here this z is the variation. Variation of the displacement u. Okay. So this z is a vector here. So all this z, I put a tilde below that to indicate that that is the variation. And this E delta is the variation of E itself, that is the green Lagrange string tensor. So this is a variation of E, and that is equal to, so this is equal to half of F transpose times del Z plus del Z transpose times F. So you can see from this particular expression that the variation is itself dependent on the displacements, because F is itself I plus del. So this is very typical of nonlinear problems, that the variation also is a function of the displacement. So typically in linearized elasticity, when you take the variation of the linear strain, correct? So if you take the variation of epsilon is equal to half of del u plus del u transpose, then the variation, let's call it epsilon delta, will be simply half of del z plus del z transpose. Right? So this, so there is no dependence of the variation of the strain, linearized strain, on the displacement. But when you do nonlinear elasticity, so like in this particular case, you will see that the variation of the strain depends on the variation of the displacement, which is z, and also on the variation of the and also on the displacement itself. So that is a complication that comes, and so a very systematic linearization of the variational formulation has to be carried out before you can actually implement it in matrix form. So as I said, that we will not go into all these details because for this particular course we are not going to get into the finite element method and things like that. So so I'm going to skip this variational formulation, but I just wanted to give you an idea about what the variational formulation looks like. Okay, so fine. Then we move on now to the energy equation. So now basically we are going to see what are the consequences of the first law of thermodynamics, the second law of thermodynamics, and so on. So before going to the first law of thermodynamics, we will first derive what is known as the mechanical energy balance. Now this mechanical energy balance follows purely from the balance of linear momentum. So no thermodynamics is involved when we are deriving this mechanical energy balance. And then later on what we will do is we will subtract this mechanical energy balance from the first law of thermodynamics to get the energy equation. Okay, so that is the flag here. So first let us derive this mechanical energy balance. So we start with the balance of linear momentum equation. So this is rho times v dot dv by dt is equal to v dot del dot tau plus v dot rho times d. Okay, so what we are doing is that we are just simply taking the dot product of the balance of linear momentum with the velocity v. Then this we can write as rho times d by dt of v dot v divided by 2 is equal to v dot del dot tau plus rho v dot d. So just I am simplifying this particular term. So you can see that this term looks something like the kinetic energy of the body. So then this term also we can simplify. So we can write this as del dot tau transpose v minus tau times del v plus rho v dot b. Okay, so this is just identity which you can prove using initial notation. So this v dot del dot tau is equal to v dot del dot tau transpose v minus tau matrix inner product with del v. So as I said, this can be easily proved using initial notation, and this is equal to del dot tau transpose v. This is nothing but the velocity gradient. So tau matrix inner product velocity gradient plus rho v dot b. And because tau is symmetric, we can write tau matrix inner product L is equal to tau matrix inner product half of L plus L transpose, and this can be written as tau times d. So this was one of the homework problems, and so we can now simplify this and write this as del x dot tau transpose v minus tau matrix inner product d plus rho v dot b. Okay, so this is the mechanical energy balance equation here. So let me just write it here. So rho times d by dt of v dot v divided by 2 is this. So this is the mechanical energy balance. Mechanical can derive the integral form of this particular equation also by integrating it over a material volume. So I'll just write that part also. Sometimes that is also useful. So, so you can write that rho times d by dt of v dot v divided by 2 times dv. So I'm integrating over the material volume here. This is equal to, then this part can be simplified by using the divergence theorem. So this actually will go to integral of tau transpose v dot n. And then if I use the definition of the transpose, this is equal to v dot tau n, and tau times n is the traction on the surface. So I can write this as v dot t times ds over s of t plus integral of minus tau times d plus integral rho times v dot b times d. So this is over v of t. And I can use the second transport theorem here. So d by dt of integral of rho v dot v divided by 2 times dv is equal to integral of t dot v times ds over s of t plus integral of rho b dot v minus tau matrix inner product d times dv over v. So this term here, this tau matrix inner product d is what is known as the stress power. So this here, so integral of this tau d dv is the stress power. So stress power. And so you can see that the rate of change of the kinetic energy of the body is equal to, so this is over here, so the rate of change of kinetic energy of the body is equal to the power due to the tractions plus the power due to the body forces, but there is an additional term also, right? So this term would be 0 if we were considering rigid body dynamics, for example, because then in that case your d itself will be 0. But if you have deformable bodies, then you can see that this additional term also contributes to the power equation, and so in that sense this is a very, very important term here. So actually, I mean, sort of we can see how to apply this particular equation to let us say, suppose let us just take a physical example and try to apply this particular equation here, right? So so imagine that you have a car, okay? So and let us say that the it is moving along this particular road here, and the so the tractions will be acting, let us say, in this particular direction here, but the velocity at this point of contact is 0, correct? And so this term is going to go to 0, correct? And also you can see that this body force is the body force is that of gravity, right? And so even this term is also not contributing to the acceleration of this car in the forward direction, right? But you know that so suppose if the car is accelerating, right, then it is clear that the d by dt of this kinetic energy is always greater than 0, right? Or if the car is decelerating, then this is less than 0, right? But then suppose if we take that almost all the parts of the car are rigid, correct, then even this term is 0. So almost. So how do you explain this particular paradox? I hope this paradox is clear, that basically if you assume that the parts of the car are almost rigid, right, and then this term is 0 because at the point of contact the velocity is equal to 0. So just it is pure rolling, right? This is a case of pure rolling, and the body force is perpendicular. So clearly this term is not contributing to this motion in this particular direction, and we are taking it to be almost rigid. So this part is 0, but the car is accelerating, right? So this term is actually greater than 0 if it is accelerating. If it is decelerating, then the rate of change of the kinetic energy is negative. So this looks like a paradox. So try to resolve this particular paradox within the context of this particular field. So you can come up with a lot of paradoxes like this. So even while cycling, for example, a similar kind of thing, that basically if you take that all the parts are rigid and the velocity again 0, body force is again in the downward direction, and then if the cyclist is able to accelerate, then where is that where is this positive rate of change of kinetic energy coming from, correct? So because if it is almost rigid, then this part is also 0. So it looks like this equation is getting violated, but of course one can explain all these paradoxes, but you can think about it and then try to resolve these paradoxes. Yeah. Fine. Okay. So we'll move on now to the first law of thermodynamics. So I'll keep this equation, the energy equation, the mechanical energy balance, because that is something that I'm going to need at a later stage. So now, so the first law of thermodynamics now. First law of thermodynamics. So what it says is that du by dt is equal to dw by dt plus dq by dt. So this u is the total energy. U is the total energy. So that this total energy includes the kinetic energy and also the internal energy of the body. The W is the work that is done by the tractions and by the body forces, and Q is the heating due to the heat sources and also the flux at the boundary of the material volume. So W is the work done, and as I said, Q is the heat supplied. So we'll now make each of these terms more precise here. So okay, so let us write what each of these terms is. So U is equal to, so let us write this. So U is equal to integral of rho of V dot V divided by 2 plus E times dV over V of T. So this is the, as I said, the total energy. So this E is the specific internal energy. E is the specific internal energy. So that is the energy per unit mass. And then once you multiply it by rho, then it becomes the energy per unit volume multiplied by the volume, and when you integrate it, it becomes the total internal energy of the system here. And this part here is the kinetic energy of the system. So this gives us the total energy within the material volume, the internal energy plus the kinetic energy, and then the dW by dt is dW by dt is equal to integral of T dot V times ds over s plus rho b dot v times dv over v of t. So this is the power due to the forces, that is the surface forces, which are the tractions, and the body forces. And finally, then your dq by dt is equal to integral of rho qh dv minus integral of q dot n times ds over s of t. So this q is the heat flux vector. Q is the heat flux vector, and this n is of course the unit normal, and and this QH is actually the heat generated per unit mass. This QH is the heat generated per unit mass. So this term, as you can see, is exactly analogous to the body force term, right? So this term you can see is like the volume term. This term is like the surface term here, like q dot n, because t is also dependent on n through tau times n. So this term is very analogous to this. This term is very analogous to this one here. Now this negative sign, that is just a matter of convention, okay, so that we will not worry about that negative sign. So basically, when you put it in your Fourier law of heat conduction, there you will put it as minus k times del T, and so that is the reason I think so basically the flux is in the direction opposite to the gradient of the temperature, and so for that reason we are putting this negative sign here. So as I said, that is just a sign convention. We will not worry too much about that here. Fine. Now we are in a position to derive the energy equation now. So first let us try to simplify this particular relation here. So we will apply the divergence theorem to get everything into a volume integral, and then we will try to simplify it here. So okay, so here first let us use the fact that q dot n times ds over s of t is equal to integral of del dot q times dv over v of t, and then the t dot v times ds over s of t is equal to tau times n dot v times ds, that times dv. This is ds only. This is equal to integral of del dot tau transpose v times dv. So this here is still over s of t. So again, I'm just applying the divergence theorem and converting it to a volume integral here in this particular case. Okay, then now we can just club everything into a volume integral. So this part here, we have seen this u is nothing but u is equal to integral of rho of v dot v divided by 2 plus e. And so the d by dt is outside this particular integral. So we can use the second transport theorem, right, and get the d by dt inside with a material derivative now, of course, on this particular thing. So if we do that, then what you will get, and also use these results whatever I have derived here, then what we will get is the following, that integral of rho times d by dt of v dot v divided by 2 plus e times dv is equal to integral del dot tau transpose v times dv plus integral rho b dot v plus integral rho qh times dv minus integral of del dot q times dv. So I have already used all these results, whatever. So converted everything to a volume integral. And now you can use localization. So by localization, what I will get, so this is also over V of t. Yeah, this is also over V of t, everything is over V of t now. This is also all of these terms are over V of t. So if I now use the localization theorem, then I will get the following equation. So rho times d by dt of v dot v divided by 2 plus e is equal to del dot tau transpose v plus rho b dot v plus rho qh minus del dot q. Okay, so this is by localization. By localization, you will get this particular equation here. Okay. So you can see, so this equation, here was the mechanical energy balance that we derived purely from the balance of linear momentum. Just by taking the dot product of the balance of linear momentum with the velocity, we got this particular equation. Then this particular equation is obtained from the first law of thermodynamics. So now if we subtract, right, this particular equation from this equation, yeah, so what do we get? So this is, so let me call this as 1, let me call this as 2. So basically 1 minus 2 will give us the energy equation, right, in the differential form. So 1 minus 2 will give, so 1 minus 2, that gives us that rho dE by dt is equal to tau times d minus del dot q plus rho times qh. Okay, so this is the energy equation. Very important energy equation. So this gives us the rate of change, material derivative of the internal energy. And so again you can see that this stress power term comes into this equation. So basically the internal energy changes due to the heat input, the flux at the surface, and also this is not necessarily at the surface. This is actually at every point within the body, and this is like stress power term. Okay. Fine. So this yes. Okay. Now the next thing that we will do is that in problems in solid mechanics, it is advantageous to express all of these equations in the Lagrangian form. Correct? And so that is what we will do. So because this whole thing, you can see that all the gradients here, so for example this one is with respect to the spatial position, vector x, small x. And so we want to convert all of this to the Lagrangian formulation, right? So, so let us do that. Because as I said, that in problems in solid mechanics, it is usually advantageous to write everything on the reference configuration. Fine. So we will convert it using the standard thing, whatever we have done, that is T is equal to tau times cofactor f. So that is the pure transform, and then Q naught is equal to cofactor f transpose times Q. So these are the two transforms. So this transform is for the vectorial fields, and this transform is for the tensorial fields. So this we have already seen. This we have not seen, but it is very similar to the transform for a second order tensor here. So this is the Piola transform. Of Q. So, and So just like we had a relation between the divergences of T and tau, in the same manner we can have a relation between the divergences of Q naught and Q itself. So we'll get del x dot Q naught is equal to J times del x dot Q. So this is the relation between the divergences of Q and Q naught. And also we can write, so we can use this relation that F dot is equal to LF, correct? And so L can be written as F dot F inverse, correct? And this we have seen can also be written as tau matrix inner product times L, correct? And this L can now be replaced by F dot F inverse. So this we can write it in this way. So we will get that J times tau times L is equal to T times F dot. So I have also used this particular relation and also the definition of the transpose and so on and so forth. So all those relations I have used, and then we can simplify it to this particular relation that J times tau times L is equal to T times F dot. And we also have rho naught of x is equal to rho tilde times J. So this relation also we have. And in addition, we will define the terms E naught of x comma t, we will define as E of x comma t, which is equal to E of chi of x comma t comma t. And similarly, QH naught of x comma t is equal to QH of x comma t, which is equal to QH of chi of x comma t comma t. So this is so these are the quantities that are defined now in terms of the material coordinates x, capital X. Okay, now we are in a position to convert this particular relation to the Lagrangian formula. And so if we use all of these relations, then we will get the following equation. So we will get that rho naught. So you basically multiply this whole equation by j. Okay, so multiply this by j, and then you can see that rho times j will be equal to rho naught, and then this dE by dt we can express as del E naught by del t, keeping capital X fixed, because that is also the definition of the material derivative in terms of the Lagrangian setting. So this I can write as del E naught by del t, keeping X fixed, and then this is equal to t times F dot minus del dot Q naught. So that is because of this particular relation here, and plus rho naught times QH naught. So this is the Lagrangian version now of the energy equation. So as I said that this Lagrangian form will be very, very useful when we see the implications of the first and the second law of thermodynamics on constitutive relations for solids. Okay, so at that time this is going to play a very key role there. Okay, fine. So now let us discuss the second law of thermodynamics. So the second law of thermodynamics is a very tricky subject in some sense, very not very precisely formulated in some sense. So it's a very difficult topic in some sense. But at least let us try to give some physical idea about why the second law of thermodynamics is required. Okay, so you imagine that you bring one hot body in contact with a cold body, correct? So suppose imagine that it's a heated piece of iron and you are bringing it in contact with ice. Okay, so now we see, this is just a matter of common experience, that the ice will melt because you are bringing it in contact with a hot piece of iron, correct? So the heat is clearly flowing from the hot body to the cold body, right? So this is of course just a spontaneous flow of heat that we are talking about here. So actually it can also happen that the piece of iron becomes hotter and the piece of ice becomes colder, right? So I hope the situation is clear that basically you are extracting heat from the ice now and putting it into the iron. So actually if you think about this, this does not violate the first law of thermodynamics, because whatever heat is lost by the ice is now going into the piece of iron. So you can see that although it doesn't violate the first law of thermodynamics, it is against our common experience, right? That where we see that the spontaneous flow of heat is from the hot body to the cold body, and so just the first law of thermodynamics is not enough to show us in which direction the heat is going to flow, right? And so that is the reason, to bring in this directionality of the heat flow, we need a second law of thermodynamics, right? And so this second law of thermodynamics will now tell us that the heat can only flow from the hot body to the cold body. Okay. Now you may say, what about refrigeration, right? There we are actually cooling something, isn't it? So but there you have to see that we are doing work there, right? I mean, there is a compressor and so on and so forth. So here we are talking of a spontaneous flow. That means there is no external work that is being put in. So of course, if you put in work, then of course you can lower the temperature. So that is not the issue here. So like in a refrigerator or in a air conditioner and things like that. So we are not talking of the situation where you are inputting some work due to some external source. We are talking of a spontaneous process. So in a spontaneous process, the heat can only flow from a hot body to a cold body, right? So basically that is in a nutshell the physical motivation for the second law of thermodynamics. Now let us try to give a mathematical statement. So as I said, that giving a precise mathematical statement for the second law of thermodynamics is very, very tricky. Okay, so I mean, so basically there are lots and lots of verbal statements of the second law of thermodynamics, such as the Clausius statement and so on and so forth. But basically, trying to convert that to a mathematical statement is, as I said, very tricky. And so there is no one clear formulation. There are lots and lots of different types of formulations for the second law of thermodynamics, but we will present one that is probably the most widely used. So you can take a look at the book by Silhavi. So there is one book by Silhavi on thermomechanics. So maybe this has a very, very detailed discussion on the mathematical formulation of the second law of thermodynamics. But as I said, that I mean, even here also you can see that actually, there are no very precise definitions of the entropy function, as we will see now. Okay, so first let us just look at what is the classical definition of the entropy function. Now, so we need to introduce what is known as an entropy function. So the classical definition of this entropy function is that, so specific entropy, so let us just talk about this specific entropy. So in the classical literature, it is defined as dq reversible by theta. So this theta is the absolute temperature, and this dq reversible is, so if you replace that actual process by a reversible process, then so reversible again is a little tricky business here. So the reversible means you're talking of infinitesimal changes, so that you can always come back to the original state. Okay, so that is what we mean by this reversible process. So the definition of the entropy in the classical framework is something like this, that you replace your actual process by a reversible process, and then whatever is the heat input into that reversible process, if you divide that by the absolute temperature, then that gives you the d eta. So, so here actually this definition is not very satisfactory because it is in terms of these reversible processes, whereas you know, all the actual processes are irreversible, right, or dissipative processes, and also it is not very clear what is meant by these d etas and dqs and so on. So I mean, ideally we would like everything to be in terms of material derivatives and things like that, which are, you know, appropriately defined mathematical constructs for a continuum. So ideally speaking, that is what we would like. And so this definition is not very satisfactory, and we would like to replace it by something that is more mathematically rigorous. Fine. So so we will simply adopt what is known as this Clausius-Duhem inequality. Clausius-Duhem inequality, which says that there exists an entropy function, eta, such that integral d by dt of integral of v of t times rho eta times dv is greater than or equal to rho qh by theta times dv over v of t minus integral of q dot n divided by theta times ds over s of t. Yeah. So this, so basically, I mean, so this actually all is given in very great detail. This whole thing is discussed in very great detail in this book by Silhavi. So basically, it just says that an entropy function exists. So it doesn't give like a precise definition of what the entropy function is, right? Like here, there is at least some formula for finding out what entropy is, but here it just says that there is some such function which satisfies this particular inequality here. Okay, so it doesn't give a precise function, a precise definition for the entropy. So then you may ask that how does one actually then compute the entropy in a given situation? So actually, so what we do is that we specify the entropy function through a constitutive relation. Okay, so later on we will see when we do thermoelasticity that basically eta will be some function of e comma theta and so on and so forth. Okay, so that we will see at a later stage. So basically we do not give a very precise definition of the entropy at this stage, but later on we will give constitutive relation for that in terms of some basic kinematical variables, and then of course this constitutive prescription will change, right, depending on the kind of material that you are considering. And so this is something that would be appropriate for an elastic solid, but for a fluid it can depend, let us say, on the density and the temperature and so on and so forth. So I mean, depending on the type of material, we will have different constitutive relations. So the whole computation of the entropy is done after we write the constitutive relation for that entropy. So at this particular stage, we do not give a very precise definition of the entropy function. That will be done later. But here we just say that there exists some such function, mathematically speaking, which satisfies this particular inequality. So all this may seem a little bit too vague, but if you read this book, you will see that there are several different viewpoints when it comes to the second law of thermodynamics, and so there is no one unanimous picture that emerges for defining this. But as I said, that this Clausius-Duhem inequality is probably the most widely used inequality or most widely accepted inequality in the literature, and so we will just use this for our purposes here. Fine, and so you have to remember that this is an inequality, and basically you will get inequality if and only if the process is reversible. Okay, so reversible, as I said, that basically you are talking of very small infinitesimal changes. Okay, and so no process actually, no actual process is actually reversible, but as I said, that is just like an approximation that we make, and so in any actual process you will have strict inequality here. So equality, let me just say that equality if and only if process is reversible. Reversible. So that is the idea. Okay. Then after this point, now again, as usual, we want to convert this to the partial differential equation form, and so we will use the localization theorem after converting all these surface terms to volume terms here. So if I do that, then what I will get is that eta dot is greater than or equal to QH by theta minus 1 by rho times del dot Q divided by theta. This dot will denote the material derivative, and so I will use this notation very often, because otherwise the notation sometimes gets very cumbersome. So I will use this. So just like I use f dot, so this is also df by dt, right? In the same way, whenever I am denoting material derivatives, so I will denote it by a superposed dot in many cases. So not always, but in many cases here. Okay, this actually, you may be wondering how we got this from the localization theorem. So this is from localization. So actually the localization theorem was for only for the case when we had equality here, right? But the localization theorem can be extended to the case when there is inequality also, and so this is from that extended localization theorem. Yes. So this let us simplify this particular equation here, which is the Clausius-Duhem inequality. Now, so we'll call this as the Clausius-Duhem inequality, and so let us simplify this now. So you will get that eta dot is greater than or equal to QH by theta minus 1 by rho theta del dot Q plus 1 by rho theta square times Q dot del theta. And we also will find it very convenient to introduce what is known as the free energy function. So the convenient to introduce the free energy function. That is xi. So we'll call it as xi. That is equal to E minus eta theta. So this is the definition. So E is the specific internal energy, eta is the entropy, and theta is the absolute temperature. So this is the so if you so actually, I mean, it's just a change of variable. So it's just that, I mean, it doesn't really resolve anything at a very fundamental issue. Just that instead of expressing things in terms of E or eta, we find it convenient to express them in terms of the free energy. So later on we will see that this xi can be identified with the strain energy function and so on and so forth. So in that sense, it is very convenient to introduce this xi. So if I take the material derivative of this, so E dot will be xi dot plus eta dot theta plus eta theta dot, and if you substitute it into the energy equation, so substitute into the energy equation, then what you will get, substitute into energy equation, then we will get following. Eta dot is equal to 1 by theta of QH minus 1 by rho times del dot Q plus 1 by rho times tau times L minus eta theta dot minus psi dot. So this is the energy equation in terms of psi dot. And so yes, and similarly we can also write the second law in terms of this psi dot. So similarly, the Gaussian inequality, Gaussian inequality in terms of this psi can be written as psi dot plus eta theta dot minus 1 by rho times tau times L plus Q dot G divided by rho theta is less than or equal to 0, where this G now is equal to del x of theta is the temperature gradient. This is another notation, temperature gradient. So do not confuse between this Q and the G. So this Q is the heat flux, G is the temperature gradient. Okay, and the temperature gradient is with respect to the spatial coordinate small x. Okay, so this is G here. Yeah, so we can express it in this particular way here. Alright, and as usual, we would like to express both these equations in terms of the material coordinates, so that is in terms of the reference configuration variables here. Again, for solid mechanics problems, it would be convenient to do that, and so let us do that. So rho naught is equal to rho tilde times J, then tau times L. So this part is very similar. We have already been through this. So this part is very similar to the energy equation. The derivation for the energy equation with respect to the reference configuration. And so this part is almost identical. And then Q naught of x comma t is equal to cofactor f transpose times Q, and del dot Q is equal to J times del x dot Q, and again now we need to define certain additional terms. So G naught we will define as del x of theta, so that is equal to F transpose del x of theta, which is equal to F transpose of G. So that is this G naught is this particular term here that is defined on the reference configuration. Then psi naught of x comma t is equal to psi of x comma t, which is psi of chi of x comma t, and then q. So this is eta naught. So eta naught is of x comma t is equal to eta of x comma t is eta of chi of x comma t, and theta naught, the last term here, so theta naught is equal to theta of x comma t, which is equal to theta of chi of x comma t. So these are all now the Lagrangian variables, and now you can write the energy equations in terms of the reference configuration variables here. So let us first write this particular equation in terms of the Lagrangian framework. So you will get del eta naught by del t, keeping capital X fixed, is equal to 1 by theta naught of QH naught minus 1 by rho naught of del X dot Q naught plus 1 by rho naught of T times F dot minus eta naught times theta dot naught minus xi naught dot. Again, all the dots are material derivatives, right? So this basically, let us just take this xi naught dot would be, this xi naught dot would be del by del t of xi naught, keeping capital X. So because so that is the usual definition of the material derivative here. Okay, so that is so this equation corresponds to this one here, and then similarly corresponding to this equation, the material form or the Lagrangian form is as follows. So you will get that xi naught dot plus eta naught theta dot naught minus 1 by rho naught of t times f dot plus q naught dot g naught divided by rho naught theta naught is less than or equal to 0. Okay, so that is the Lagrangian form of this one. So as I said that these are the forms that we will prefer when we study the restrictions on constitutive relations imposed by the second law of thermodynamics at a later stage. So that is towards the end of the course, we will study the restrictions on a thermoelastic material for a solid, so thermoelastic solid, due to the second law of thermodynamics, and also material frame indifference and so on and so forth. And for the case of fluid mechanics, we will directly prefer the Eulerian formulation. So as I already said that the Eulerian formulation is preferred in the case of fluid mechanics problem. So we will use these equations when we are talking of the, or when we are trying to derive the restrictions on the constitutive relation for a fluid, and we will use these two relations when we are discussing the restrictions on the constitutive relations for a thermoelastic solid. Okay, so that is the picture here. Fine, I think so this sort of completes the discussion on balance laws, and now we will move ahead to the discussion of constitutive relations. And this is also a very, very important topic, and we need to bring in the concept of a frame of reference. Okay, and so this concept is not very trivial, and so try to explain these things in detail now. So let us start our discussion of the constitutive relations now. This is the 4th chapter in the book. So, constitutive relation. So first let us see that what is the need for constitutive relations, right? So what are the unknowns first? So you have rho. So unknowns are as follows, right? Unknowns that we are trying to solve for. So rho, that is one unknown. Then u is 3 unknowns. Then tau is 6 unknowns. Okay. Then we have theta. Then e, eta, and q. So this is also one unknown. This is one unknown. This is one unknown and this is three unknowns because Q is a vectorial unknown. So this is, you will see that this is 16 unknown, right? And how many equations do we have? So we have the balance of mass, first of all. So, so let us write the equations here. So the equations. So balance of mass. So that is just one equation. Balance of mass. That is d rho by dt plus rho del dot v equal to 0. So that is just the one scalar equation. So that is just one equation there. And then we have linear momentum. So linear momentum. This is one equation. This is one equation. This is three equations. So that makes it 4. And you can see that the balance of angular momentum is implicitly used up because that just implies the symmetry of the stress tensor. And already I have indicated only 6 components. So already it is used up. The symmetry of the stress tensor means that we have already used up the angular momentum principle, and so we don't have anything additional there. And we also have the energy equation, right? So energy equation is there. So energy equation, so that is another one equation here. So we have only 5 equations, and but there are number of unknowns is 16, correct? So that means we need 11 more equations. That closure, right? The closure means we need to have as many equations as unknowns, and so this closure is provided by what is known as the constitutive relation. So just to give some examples, so basically tau is equal to tau hat. So this is just an example. I mean, this is not. This doesn't. Whatever I'm writing here does not cover all possible materials. This is just for some typical material. It could be something like this: F theta, then Q would be equal to Q hat of rho theta, then E would be E hat of rho theta, and eta is eta tilde of rho theta. So I mean, as I said, this is just one typical example. It need not be always this. It could depend on the rate of the deformation gradient and so on and so forth. So we'll not get into that. But this is just one example that basically we have constitutive relations which will give the closure now. Okay, so now you will have 6 plus 3, so that is 9, 10 and 11. So now these are the 11 additional equations in addition to these equations that will provide the closure now for the constitutive relation here. Even physically speaking, it is clear that we need to bring in the type of material that we are discussing, right, in order to solve a particular problem. So, for example, how rubber behaves is very different than how steel behaves. For example, if you have a given loading, then the behavior of these two materials is going to be completely different from each other. Or if you have a fluid, then that behavior is going to be even more different, right? So even from a physical viewpoint also, it is clear that we need to bring in the nature of that particular material into the analysis, right? And that nature of the material is brought in through the constitutive relations, right? So that is so both from a mathematical viewpoint and also from a physical viewpoint, it is clear that we need something like these constitutive relations here, right? And so as I said that I mean, these are not hard and fast, these are just examples that I am giving at this particular stage, and then later on we will discuss this in very great detail for the case of thermoelastic solids and also for the case of fluids. So that part, as I said, that we will discuss that towards the end of this particular course. So, so in order to study constitutive relations, we need to bring in the concept of a frame of reference now, and so let us discuss that concept of a frame of reference here. So because the constitutive relations will be required to satisfy what is known as material frame indifference. So that is some axiom that we will introduce at a later stage, but at this stage then let us just introduce this concept of frame of reference here. So frame of reference. So the way to define it is just the background against which observations are made. So basically, the best way to understand a frame of reference is just through examples. Okay, so imagine that you have an observer on the ground, and then suppose if there is a pilot in an aircraft, and then he is traveling with some velocity with respect to the observer on the ground, and then imagine that the pilot is conducting some experiment in the airplane, and so now the observer on the ground is observing a certain stress state in that body which is in the airplane, and then the pilot is also observing some state of stress in the body which is in the airplane, and so you can see that basically the body is the same, right? That is just some body on which there is some load, but there are two observers now who are observing this particular phenomenon. There is one observer on the ground, and then there is the pilot in the plane who is also observing that particular body. So you can think of it in this particular scenario. We have, so let me just call this as X, Y, and Z, and this we will call as the O star frame of reference. And let us talk of the other frame of reference. So that is in completely arbitrary motion now with respect to this O star frame of reference. So let us call that as the O frame of reference. O frame of reference. And so this is X, Y, and Z. Okay. And as I said, that both of them now, so there are these two observers who are in arbitrary motion with respect to each other. They are both observing a particular body, okay, and the state of stress or whatever it is of a particular body. So we need to now define what we mean by the position vector now as seen by the two bodies. So let us call this vector which connects the origins of this O frame of reference with respect to the O star frame of reference. Let us call that position vector as C of t. And then the position vector of a point. So this is the body that they are observing, let us say, and then take a typical point within that particular body. Let us call the position vector of that particular body with respect to this frame of reference as x star, and the same position vector with respect to the frame, coordinate frame that is attached to the O observer as x. Okay, and so the relation between x star and x will be of this particular point. So x star is equal to q of t times x plus c of t. So this q of t is a proper orthogonal tensor. So this q of t is a proper orthogonal tensor or rotation. So we will come to how to actually compute this q given the orientations of this xyz, capital XYZ, and the small xyz. We will come to that, but at this particular stage we just write what the property of this q is, and then the c of t is just a vector, right? This belongs to R3 as usual. So okay, so now we have to be very careful about how we interpret this x star and x. Okay, so this x star is the position vector with respect to this coordinate system that this observer has adopted. Okay, and x is the position vector according to this coordinate system that the O observer has fixed on. So many times if you read some of the undergraduate textbooks, for example, then there probably books by Shames, for example, on statics and dynamics. If you take that book, for example, he will define x star as equal to x plus c of t. Okay, so this q of t is missing in that. But you have to understand that there, in that case, his x is also measured with respect to this xyz. Okay, and then this equation would be correct if your x is also measured with respect to here. But the way I am writing this particular x, this x is actually measured with respect to the xyz, the small xyz coordinate frame, and this x star is being measured with this. And since this coordinate frame is rotated with respect to this one, we need to bring in that rotation through this one here. So this equation would be valid if both of them were using the same coordinate system. But in the way we are defining it so that they are both using their own coordinate systems, and then the q accounts for the rotation of one of these coordinate systems with respect to the other coordinate system here. So actually this viewpoint is more convenient as compared to the viewpoint that is followed in these undergraduate type books. That is because, see, suppose if there is actually a pilot who is conducting an experiment, he would like to use his own coordinate system, which is fixed to his own plane, not a coordinate system that is fixed to the ground. Correct? So it is much more convenient for him if he is conducting some experiment to use his own coordinate system. And similarly, for an observer on the ground, it is much more convenient for him to use his own coordinate system rather than a coordinate system that is fixed to the plane, right? And so it is much more advantageous to adopt this particular viewpoint rather than this one. So that means both of them use their own coordinate systems rather than using a common coordinate system. The reason maybe why they do not use this viewpoint at an undergraduate level is because maybe they want to avoid introducing rotations and things like that, because then it can get a little bit mathematically a bit difficult, and so maybe that is one reason why they may not be introducing this at that particular stage. But anyway, we will not go into that. We will now see how to actually compute this q and so on. So this, so if I call the basis vectors of this xyz as, so let us call it as E1 star. So this is the base, these are the basis vectors, E1 star, E2 star and E3 star associated with the O star frame of reference. And if the basis vectors here are E1, E2 and E3, then we will see that your Qij is given by Ei star dot Ej. Okay. So that is the way you find the components of this particular thing. So I'm not going to go into the derivation of this, how we derive this component, because that is given in the book, and plus you can easily figure it out on your own. So we will actually see this through by means of some examples. So that will make the situation much more clearer. So that I think we will do the next time. So at this stage, let us just take this as the definition of this one.